So in this video, we're going to have some fun with the Raspberry Pi SenseHAT board. So what I have here is a Raspberry Pi 3B Plus, and I've got a kind of cool configuration on it. This has got a universal power supply, battery-powered backup board. That's this guy right here. And I power it with this micro USB, and it charges the battery. And it's the battery and the controller on it that supplies power to the Raspberry Pi. So I turn the Raspberry Pi on and off with this little button, which is really pretty cool. So the board on top is called a SenseHAT. Now this is developed by the Raspberry Pi Foundation, and it actually flew on the International Space Station. It's got a number of really cool features. I have an 8x8 matrix of RGB LEDs. Each one of this is an RG and B. That's PWM controlled, so I can control the color mix and the intensity on this whole matrix. You'll see this later. I've got a number of chips on here. I've got a analog chip. I've got a temperature humidity chip. I've got a motion orientation chip. That's this guy right here. And I've even got a up, down, left, right, push, enter joystick control right here. So I've got a lot of things on this. This is a great way to start. This is all I2C. All of these devices are on a separate I2C bus addresses, all on the same bus, but different addresses, as you'll see. And we're going to come in here and start playing with it. So it's a lot of fun. It's pretty cool. And it's got a compass, got accelerometers, it's got an orientation. So let's take a look at what we've got here now. So I've got output, and I'm using the SenseHAT library of SenseHAT dedicated, let's see, where are they? Dedicated nodes that are in here somewhere. Ah, there we go. SenseHAT inputs and outputs to the SenseHAT. Okay? You'll see how that works. We have a number of different families. So I actually have inputs for the environment, like temperature, humidity, pressure. I have outputs like or inputs from the SenseHAT for acceleration, X, Y, and Z, roll, pitch, and yaw, compass. I have the joystick input, and then I have output. I can send text to the matrix, and I can actually scan the addresses. So let's take a look at what that is. That is I grab that from the I2C, and I can see what addresses I have. So let's see what happens here. Let us go, to see all this stuff, we have to go to the actual dashboard of this flow. And let's open up that dashboard here, and let's paste that with a lowercase UI, and we should see a dashboard show up. And let's see, let's find SenseHAT. Okay, that's our SenseHAT family. So now we're getting a bunch of data in here. We're seeing temperature, humidity, pressure. I'm getting motion. I'm getting my joystick, and I can scan. So I can press this button. Let's see what happens. All right, so we've got device I2C bus devices at 106. And so 106 decimal. The LEDs, let's enter text. Let's enter the text, hello world. And it's a little bit bright that you can see. Let's do something simple. Let's put in something, a big X. And it says hello world and scrolls it across with a big X at the end, unless I undo all this, and then I just leave a big X, and then it sits there with the letter X. That's the last letter. So unfortunately my camera is not cooperating, so you can't see the X very easily. But I can put in other colors, I can control LEDs, I have a whole bunch of things I can do. Now, if I look over here, look at the orientation. Let's start with the compass. That's probably the easiest way to start. I can see that if I rotate this guy, I've got a compass heading. Also, you can see the yaw. Now, if I do pitch, I can see that the pitch is moving. If I see roll, I can see that the roll degrees are changing. And if I do acceleration in the Z, in the X, or in the Y axis, I get in gravimetric units, in G's, I get the acceleration, as well as the orientation, as well as the compass heading. So that's pretty cool. I can look at the joystick entries. I can see that I press the enter key, and if I press and hold, it goes from 1 to 2 because it's persistent. If I press up briefly, I see it goes up 1, but if I'm persistent, it goes to 2, so I can see the persistence. So I can not only see which I'm pressing, but whether I'm just momentary or whether it's persistent, to the right, down, left, up, etc. So let's take a look at the flow that is doing all this. Now, here I've got some functions, which is very, very powerful. I'm going to introduce you to probably one of the most powerful next steps that you can move beyond just node-read nodes, and that's the function node. In here, you can use it to write JavaScript, and that's what we've done. JavaScript is the software language that you can customize this function node to do pretty much anything. Now let's look. This is really probably the simplest, okay? What this does is it says, I'm going to take and define variable named t. And I'm going to assign whatever comes in as the message payload, I'm going to assign it to that variable, okay? And then I'm going to make a new message payload to go out, and I'm going to call it t.temperature. And then I'm going to send it out. I'm going to return that message on the output pin. I'm going to send it out, and I'm going to send it to the dashboard to the temperature, which is, in this case, a text output. And that's what it looks like over here. It shows up, and it says the word temperature, and gives me the value, which was the payload, t.temperature. So that's how this works, t.temperature, and with a ampersand, which is to basically tack on the word DEG, capital C, degrees Celsius, and it says temperature. And I can format it in a variety of ways. I can label, value on the right, label on the left, label then immediately value, centered, right justified, or centered top and bottom. So I can do that for all of these. Same thing with the compass heading. I can just change the payload to the compass and pick up whatever payload that is, send it to the compass, and say degrees, give it the degree symbol. And that's, in fact, I've got various symbols I can use. That's how I get the degree symbol out here. And other things like percentage or millibars and such like that. So that's pretty much how the SenseHAT works. You can, in fact, do the entire SenseHAT, for the most part, without using functions. If you're clever with the switch and change modes, you can actually change the names of whatever's coming in. You can sense for it, and you can send it out to the appropriate dashboard widgets over here. So that's pretty much it for how the SenseHAT works. I'll leave the rest for you to play with, but till next time, have fun with it. So this video is going to be on our UPS board. This happens to be from a company called Geekworm. And you notice the 4 LEDs here. That gives me a rough idea of the status of the battery charge, state of charge, SOC. 1 being the lowest, 4 being the highest. So you can see this is the fully charged. And you'll have solid when it's at that level and blinking for the next level up. That shows you that it's charging and working. So, and as I mentioned on the SenseHAT video, this is the button that we use to turn on and off the Raspberry Pi from that UPS board. And in fact, I can unplug it. We can see that it's got some charge to it, but you can see that my Raspberry Pi is still running. Okay. Well, actually, let's see. Yep, the Raspberry Pi is still running, even though I'm not charging the battery. The Raspberry Pi is running all on its own off the battery. So to prove it to you, I'm going to let it sit here with no strings attached, as they say. And let's take a look at our flow here. Now, I've pre-built this to show you a couple fun things in the interest of time. The first thing I did was took an I2C scan node, and that's in our I2C group. That's the top one in the I2C. And then we're going to scan for a list, message by message, each address that shows up on the SenseHAT and UPS board as an I2C device will have its own address, and it'll show up here like so. So I have one at 28, and these are all decimal. If I want the hex, I just click on it and I see the hex value, 0x1 Charlie. That tells me it's a hex value. If you see an alpha symbol here, alpha through Fox, A through Fox here, a letter, in other words, somewhere in here, then you know for sure it's hex, because decimal doesn't have any letters in it. So this is decimal 28, 54, 92, 95, 106. And as we see, we've got the battery controller monitor is on one of these devices. Usually the documentation will tell you what it is. But let's take a look. This one is actually at 54, is what I just looked at. So I'm using the I2C input node to pull in 2 bytes from I2C address 54, all on the same bus but at a unique address. But in register 2, I'm going to pull 2 bytes, which means from register 2 and 3, I'm going to pull 2 8-bit bytes of values 0 through 255, 256 different levels or values, unique values. And together, they're going to be able to give me some information about that battery. Okay? Now, that particular address, register 2 and 3, 2 bytes, will give me the voltage that's sitting here on my battery, the condition of the battery. And what I do here is I've got a little function that sets the most significant byte and the least significant byte, because in looking at the documentation, the one that's sitting at register 2, not register 3, the first of the pair, is sitting here in the message payload 0. Okay, so let's take a look at what this looks like. If I click on a timestamp and I look at whatever this debug node is going to spit out, it's going to spit out a pair of numbers. Okay, and this set of values is correlated with that debug node off of the voltage at sub-address. Okay, so I've got an array of 2 bytes of value 201 decimal and 96 decimal. So how do I deal with that? Those two have to be interpreted to some number of volts in actual engineering units of volts. So how do I do that? I do that with a function node. And I know, according to the documentation, that I have to take the most significant byte, which is the first value, multiply it by 256, add it to the other values at the second register inside the chip, and that multiplied by 78.125, divide that by 1 million, okay, and then I convert that to 3-place precision, so I only want 3 places, I don't want 26 decimal points, I only want 3 decimal points, and that I assign that to the variable num, and then I make that the payload is the variable num, and I return that. All right, and let's see what that looks like. And that should go to something called volts. And if we go to our, let's see, I think we have to probably look at the output here at 15, here we go, volts. So we're looking at the output of IoT, because what happens was I put this widget on IoT page, the IoT tab on the dashboard, in group called out. So the output group has something called volts, but it's also got state of charge and flow rate, which we'll get to here in a second. So the volts I have a little gauge here, and it's actually reading 4.03, three decimal values here. And so I'm actually measuring volts. Here, I'm measuring state of charge. I'm doing something similar in the function and taking those, but a different formula, multiply it by 256, and then add the LSB, and then take that whole value and divide that by 256 to 2 decimal places of precision. And if we look at here, I got 2 decimal places, 93, which is percent. So the state of charge is 93%. I've already pulled down this battery a little bit by running it for the last 20 minutes. Flow rate. This tells me the relative flow rate in or out of the battery, and in percentage of the total charge. And it's another formula. I take just the LSB in this case, multiply it by 0.208, 3-place precision, and I can actually see that my flow is 31% of the state of charge, and there's a formula in the documentation that tells you how to interpret that. In other words, this tells me how much I'm using the battery, either charging or discharging, and gives me an estimate of the percent of the state of charge per hour. So it's 31%, so that means that it should last me about 3 hours at this flow rate, at this power consumption rate. Now, I mentioned that you can do all this without using function nodes. Again, code-free IoT, no function nodes. How do we do that? Well, we've got a cool specialty node that is called the buffer parser and buffer maker. So here I'm going to take the buffer parser, and I'm going to use this to actually split up this data, and I'm going to do some calculations. This tells me the type of data coming in. This is 16 bits or 2 bytes. Big endian, which means the first byte coming in is the most significant bit, has to multiply by 256. The second byte coming in is the least significant byte, and that gets multiplied by 1. And then I can multiply this by a value of 0.00078, because that's 0.78 divided, or 7.8 divided by 1 million, and it gets decimal shifted here. And I can, so in other words, I can do my math. I can do my offset and scaling, and I can do it for volts, I can do it for state of charge, I can do it for flow. So I can do it for all three. So that's what I'm doing here. So let's see what we get. So I get 3 outputs now. I get 4.145, I get 94.499, blah, 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 and I get 6.656 according to that particular formula out on that debug node right here. And that's what I get when I get the raw data, okay? And when I want to separate them out, let's clear this out. And let's hit this timestamp, and let's see what we get. We get 90%, that's 90% state of charge. That's this one, that's the output. Then 4.0125 volts, and then 13603.199999, and that is my raw data. And I don't think I've got a formula of 0.208. So this is an example of how you can use just a dedicated node to completely reinterpret and reformat one or more messages that come in that are raw data. And I have a lot of different ways to parse these out in either a single raw byte, in different byte formats, big endian, little endian, that's what the LE and BE stand for. And you can read more about it. Floating point, double precision, strings, hex values, etc. I can bring in data that's formatted in a variety of ways, bust it up, and add offset and scaling factors to it, and that's what that will spit out. And I can spit it out to a debug mode node of what I've done here. I can output it to a gauge. I can output it to another node, send it onto the internet, do whatever I want with it. So this is a pretty good example of how I can get data in from an I2C device, such as the UPS controller chip, bust it up and read it out. So I hope you've had some fun learning more about this UPS device, I2C devices, and ways to format data. Till next time.